Hello, everyone. Um, Thank you, Benji. Hello, everyone. This is Nikhil Gopinath, and I'm a VP of Engineering for ML Platforms here at Sedai. And joining me here is Tsahi Peleg, who's a Principal Software Architect at Palo Alto Networks. And what we're going to talk about today is about the problem of picking the right metrics when it comes to your observability tools. So there's a popular principle in engineering which says you can only manage things that you can measure, right? Which implies that having data to measure and monitor a system is a good thing. Now, too much of a good thing can also cause problems, right? So how much data is too much, and what are the problems potentially too much of data, too much of metrics can cause you? So we'll briefly explore that. And then Sahi will tell us how they solve this problem in Palo Alto and kind of some of the key insights and cool approaches that they did internally. And I'll also talk eventually about how Sedai solved this at a much generic approach to metrics prioritization, right? As we scale, as we work with different customers, what are the kind of things that we did to prioritize metrics and get to the right metrics? So to set this in context, Sedai is an autonomous availability and an optimization platform for your cloud infrastructure. So essentially what that means is we manage your cloud, your infrastructure, your applications, your microservices autonomously and make sure that they're available and optimized. We don't do that in isolation. We build that by building on top of observability platforms. CloudWatch, Prometheus, Datadog, just to name a few, but there's plenty of others more that we work with, right? So this is observability platform is one of the foundations of what we build on. And the key things that these platforms provide us is metrics. Metrics comes in various size and forms. There is system metrics, traffic metrics, application metrics, there's topology information, and tickets. So we get data and signals from multiple forms from these platforms. Now, just to settle that in a little bit more, right? Here is a snapshot of what Sedai's architecture looks like. On the left, we have a bunch of APMs and monitoring systems like Datadog, New Relic, and so on, which provides us a lot of information, very high resolution, detailed information about everything that's happening within your system. Also bringing us information and also for us to push information are notification providers. So we do push and pull information from Slack or PagerDuty or other systems like that, right? Then there are ticketing systems like BMC, Jira, ServiceNow, and of course, we have the cloud providers, right? Providing their own data, their own topology, and a bunch of other information and metrics along with the flow. And also, of course, we integrate with runbook automation systems like Stackstorm and Rundeck and so on, right? So this is just to kind of, again, give the context of what we are working on and the magnitude of the problems that we typically face. So let's talk about the problem of metrics overload and having too much metrics. So to set this in context, with working with APMs, APMs are good, and we all understand and realize the value of having data flown into your systems for monitoring through these monitoring providers. Now, when they started out, you only had applications that are deployed in VMs and traditional monolithic siloed applications. But today, a definition of an application is much broader, right? So when we talk about an application, it could be a microservice, a single service could be treated as an application, right? Then you have Kubernetes container-based deployments, you have serverless functions, right? So the definition of applications is changing and evolving. And that means each one of these applications is now generating the same volume of information and metrics that your previously single monolithic applications used to. So there is a multiplication and exponential growth in the number of applications, which leads to a growth in the amount of metrics that comes from these systems. The immediate challenge with this is if you want to use these metrics to build any kind of models or analytics or make any predictive guesses into what could be happening with your system, you are dealing with a lot more metrics. And just as a typical number, right? A single monitored application through New Relic generates up to 135 plus metrics. And talk about a system with thousands and tens of thousands of serverless applications. That's an exponential increase in the number of metrics we are talking about. Now, majority of this data is either redundant, irrelevant, and noisy. So what I mean by that is a lot of this data that comes from these systems are not correlated to anything else, right? These are useful data when you explore, when you look at them one by one. But then again, there would be key insights into that, but again, they might not be exactly relevant to a particular problem that you're trying to identify or a set of issues that you're trying to prevent from happening. And then there's the opposite problem too, right? So many of these metrics are directly correlated with each other, right? It's network input versus network bytes, right? They all tend to be almost exactly the same, right? So do you need both, right? Sometimes you may not, right? And again, it's hard to answer that in a very general manner, but then you see that there are redundancy in the data building up to duplication of information. And then signals, of course, can be noisy, right? For lack of due to multiple reasons, right? Maybe the sensors aren't as tuned as it should be, or there is inherent noise in the system, right? So there are data that has inherently no value that actually can lead to any kind of predictive insights. The other thing is, so now as metrics grows, as the number of metrics that you look at increases, how do you use these metrics to identify root cause, right? How do you know what is the metric that actually led to something else changing, right? How do you step back in time, right, and find out what was that fundamental thing that caused and triggered all this outage or caused a problem in your system, right? So as the number of metrics increases, doing root cause analysis and identifying the root cause becomes a much more harder and complicated problem. And the same happens when you flip the temporal aspect, right? You have some metrics now. How do you predict what's going to happen? And what metrics is this going to impact? And what does it mean down the stream for you, right? Again, as the number of metrics grows, that becomes a much more harder and complicated problem to solve. So that's just baselining some of the challenges with the volume of metrics and why it's important to prioritize metrics is, right? So with that, I hand over to Tsahi, and he'll tell us about how they overcome some of these challenges in Palo Alto. Over to you, Tsahi.
Thanks, Nikhil. Hi, everybody. So I'll spend just 1 minute to explain a little bit about Palo Alto Networks in case somebody doesn't know, didn't hear about us. So it's a leading global cybersecurity vendor. We are specializing in various fields like network security, automation of security operations center, cloud security, and also we have a security research unit. So we are kind of developing every part of your security solution as a platform, hoping to be partners for managing the security challenges of different enterprises. If you can go to the next slide. Then personally, I'm working as part of the SASE group in Palo Alto Network. SASE is one of the solutions that we are providing to our customers in the last few years. It's actually a revolutionary approach to enterprise networking. It's a new model for enterprise networking, which grew significantly in the last few years because of the increase in remote workers and also in cloud-based applications. The general idea is that your enterprise network and enterprise security is delivered as a service in the cloud. So we have firewalls, routers, and all the other network and security appliances for your enterprise network running in Palo Alto Networks cloud and offered as a service to our end users so that they can connect to their enterprise network either as mobile users or from branches and connect to their enterprise applications running in the data center, in the public cloud, in the internal cloud, and so forth. So this is the solution we are working on. And what I wanted to spend the time and talk about a little bit is the challenges that we saw with regards to observability and how do we monitor this solution? How do we know that the solution is up and running? How can we reduce the number of noise that we're getting by measuring too many metrics that are emitted from this solution? So if you go to the next slide, then this is what the solution is actually comprised on. We have SD-WAN routers that are running as VMs in the cloud. We have firewalls, Palo Alto Networks firewalls running as VMs in the cloud. These pieces are interconnect with IPsec tunnels that interconnects routers with firewalls and actually implements your enterprise network. And we have Kubernetes-based control plane and data analytics platform that actually controls all of these enterprise networking solution. We also have a serverless-based control plane for some of the functionalities, mainly for managing the policy of this solution and for orchestrating firewalls, SD-WAN routers, and so forth. Now, each of these components, as you can guess, emits many metrics to our monitoring solutions. Today, we use Datadog, Google Cloud Monitoring, and the Influx Tick Stack, and we have a few more solutions. And each parts of these complicated systems is emitting a lot of metrics to our monitoring solutions. And one of the key challenges that we had internally is trying to figure out which of these metrics is really relevant for us, which of them can be something that could indicate a real problem that we need to handle. And if you just monitor all of these metrics together and build threshold-based alerts on them, it's very easy to get to a point where you get too much noise, and it's very difficult to root cause and to understand what are real problems versus things that are outliers or not a real issue. If you can go to the next slide. So when we started looking at our metrics, I think the first thing that everybody are starting to look at is the golden metrics, these key metrics that represents the state of the system. So if you look as an example at our firewalls, which is one of the components in this system, so they emit metrics that falls into these 4 golden metrics categories. They emit metrics about throughput, which in the context of firewalls can be the number of config changes and also the actual traffic throughput that goes through the firewalls. They emit metrics that designates errors, whether they are errors for the APIs that they expose and config errors, or whether they are logged errors in our firewall logs. They obviously emit metrics that relates to the latency, starting from the actual security processing latency, network latency, but also the APIs and config changes latency. And obviously, they have the saturation metrics as CPU, memory, and so forth. So we have around 100 metrics that are getting emitted by our firewalls today. And obviously, monitoring all of them is something that we actually do, but setting alerts based on thresholds for all of them is going to be pretty noisy. And taking into an example, errors, for example. So if you monitor errors based on errors in your log files, this could be pretty noisy, and a lot of them are not really indicating something that you immediately need to take action on, because some of them can be validation error for actual API usage of the end customer and so forth that doesn't really require SRE to be involved. So when we looked at all of these metrics and we tried to build a monitoring solution that scales well and doesn't feel too noisy, what we did is we built a solution that is based on multiple steps. So we first collect all of these metrics. We have all of them available in one of our databases. We can see them whether with Google Data Studio or with Grafana. But for generating alerts, the first thing that we did is we filtered the noise. So for example, for errors, we filtered the errors that are not representing a real issue. So for example, if there's a user validation error in our log, we don't count it to generate an alert. But if there is a critical service connectivity error, we definitely do. Now, once we take all of these different metrics and alerts that we generate after filtering this noise, the first thing that we do is we try to aggregate them. So per resource, in this example, per firewall, we just aggregate all of the alerts that the system can identify per firewall periodically, and then we prioritize them. So for example, if there's an alert on a crashing service or an alert on a very basic system resource that is unavailable, we prioritize it on top of the other alerts, and we try to handle these first. And when I say handle, the first thing that we try to do in order to reduce the noise from the SRE team is to try to see if we can auto-remediate. The easiest example is a service that is crashing. Maybe we can reset some of its caches or configs and restart the service. But we have a lot of remediation playbooks that we are trying to run on these firewalls if we see that they are in a critical condition before we actually notify the SRE on alerts that could not be remediated. So using these mechanisms of aggregating the alerts per resource, then analyzing the resource status, trying to auto-remediate it before notifying the SRE on an existing firewall with an alerty condition, this is what we basically did in order to reduce the noise. There's one more slide which summarizes, I think, our monitoring approach. The first thing that we identified internally, that the monitoring, like figuring out the right monitoring, is a journey, because even though we thought that we identified all the key issues that could imply that there is a customer experience issue, we always identify new metrics and new things that we didn't manage to identify before, and we always identify new metrics that seems to be noisy. So in order to solve this problem, we are working in like a cycle of an endless loop, if you will. First of all, using our aggregation and automated remediation policy that I talked about, and then we try to measure the efficacy of that auto remediation. Items like MTTR, how much time it takes to resolve a problem. Items like how much noise alerts generates, and also misdetections that we manually analyze against things that we discover from our customers. And given that input, we are constantly trying to prioritize on our metrics, to revisit them and to see whether we need to change our policy in what's noisy or what is missing in our monitoring solution.
All right. Thank you, Tsahi. It's very interesting to note that how different teams are trying to solve the same problem abstractly converges towards a very similar solution, right? It's that's sort of what we started out too with Sedai, right? We started filtering data out and eliminating noise, but we had some kind of unique challenges on top of what you're facing, right? Because we work with different customers. So the monitoring providers that they have are very different, right? So it's very hard for us to normalize data across providers. So that was one big challenge we had. Also, we deal with many different kinds of resources, right, on multiple cloud platforms. So that also adds to the dimensions of data when it comes to managing the data and getting the signals out of them. And of course, we are not collecting data for any post-processing or doing batch-based analytical analysis, right? This is more of real time. When the data comes in, when the metrics comes in, you need to make a prediction and you need to find out what's happening and what can we do about it. So to kind of help us with framing those constraints, we came up with this data hierarchy. So we started working with this framework because this is pretty common with autonomous systems. So we adapted this a little bit. So what you have is, at the basic level, you have raw unfiltered data, right? That comes out of all these different monitoring systems. It just streams into your data center. But then you need to, and just like you said, we aggregate that data, summarize it, and make it more consumable, right? So make it more meaningful and extract information out of it. Now, once you have information, then you move up the hierarchy and try to extract patterns, trends, and insight, right? So this is where you get the insight from the data, the knowledge from the data. What is that data actually trying to tell you, right? So this is much more filtered, condensed, and meaningful for someone to consume. And now, once the knowledge is available for you, you can kind of accumulate them into your wisdom, right? You know what is happening. You are aware of your surrounding. Now, how do you actually use it to make changes? How do you make decisions out of it? How can you explain what you just learned from the knowledge, right? And what kind of actions can you do on that? So we came up with this framework, and what I'm going to talk in the next couple of slides is that movement from data to information, right? That's where we actually do the metrics prioritization. So it's in that level of this hierarchy that we are going to talk about. So like you said again, we had different ways of classifying metrics, right? Golden signals is pretty standard across industries. You have other methods like the use method, red method, Valley, which again came from Google, right? So these are different ways to look at your metrics and kind of classify them. But what we realized is none of this actually fits our mental model and how we wanted to approach metrics and use that for prioritization. So we came up with a slightly different way of categorizing metrics. And we borrowed heavily from the practice of data science and machine learning and statistics to influence this thought process. So what we look at on one side is the input metrics, right? So these are the independent metrics or the independent variables for the data scientists out there, right? So we look at things that is completely outside of your system, that has no that is driven completely by external systems, right? So most of the time, this is like traffic coming in or messages that's passed to your system, or uh, or events or uploaded file sets. We don't control that, right? So that's, we treated that as the input variable, the input matrix that comes into the flows into the system. And at the other end of the pipeline, we had the primary metrics, which are the things that you actually care about, like timeouts, throttles. These are the things that you want to actually, you worry about, you spend your nights waking up about, right? And this we classified as the primary metrics. And where it gets interesting is connecting these input metrics with the primary metrics are all the secondary metrics, right? Your saturation metrics mostly, right? This is your CPU, your file IO, your memory usage, right? These are all hidden variables that actually links from your input metrics to the actual metrics that you care about. So this kind of classification helped us think very methodically about all the metrics that we have and build up this correlation chain, right? So you start with input metrics, which impact the secondary metrics. The secondary metrics in turn impacts the primary metrics. So the question here is, how long does it take for an input metric to impact your primary metrics, right? So how does it go through the correlation chain and cause that causation or that correlation link? So the key insight we had is correlation between these metrics are all time shifted. That there is a relationship between them, but there is a time lag associated with them. So the challenge here is, how do you find this correlation between between metrics with this time shift? So our approach to do this is take all the metrics out there, right? All the streams of metrics, and go through a process using machine learning to kind of auto those metrics as either primary, secondary, or input metrics. And then we take each of those metrics, eliminate the static data, the nonlinear data, the noisy data, and then compress the correlated ones, right? So this is the step of going from data to information, right? You're eliminating noise, you're cleaning up the data and getting the ones that's actually meaningful. And then you run a correlation analysis with time shift, right? And I'll explain what that's in just a moment. But you do that across all the combination of metrics that's flowing in. Then you rank those metrics and find the correlation score and use a reinforcement learning technique to kind of continuously evolve this metric prioritization process. So what you get out of this entire process is a much smaller curated list of metrics that's actually shows the input metrics behavior, the output, the primary metrics that you really care about, and then also the relationship between them, right? So that's our process of metrics prioritization. So here is just a classic example of what you see, right? You have traffic, you have CPU, you have discretes, right? And they are all, there's pattern there, but it's hard to discern what those patterns are. But using time shifting and then finding the correlation between them, this is what we get after that alignment, right? You see that CPU, the traffic predicts what happens with discretes, right? And discretes eventually predicts with what happened to CPU, right? So if traffic is your input metric and CPU saturation is what you care about, then discrete is something that can actually be that hidden variable between those, right? So this kind of analysis helps us find those correlation and those link between those metrics, and then limit the metrics that we look into a more manageable finite set. So overall, the outcome of this approach has been phenomenal for us. We were able to look at pretty much 90% of the metrics and see that most of them are redundant or noisy. And the true signals are hidden in approximately around 3% of the metrics. But this is not a static number, right? We continuously look at every single metric and then look at the resolution of those metrics, adjust them, do this process iteratively, and find out what is that 3% of metrics that's actually relevant, and that helps us make this prediction about what's going to happen and improve your availability and optimize your resources. So this helps us improve the signal to noise ratio, and because of this approach, we are able to handle significantly higher volumes of metrics and get to the right one, and also helps us scale the platform. So that's pretty much what I want to kind of talk about here. So I'll just open the floor for any questions and any comments anyone want to make about this topic. All right, I see a question pop up here which says, don't we lose hidden signals in data if you don't look at everything? Yes, that's a very insightful question to ask, right? So yes, sometimes there are metrics that we might drop and might have been a good predictor of what's happening, right? But then the interesting thing is we go back and with the reinforcement learning technique, we look at the actual events or the outcome that happened and see, okay, there was this hidden variable in a matrix that we dropped that could have actually predicted this, right? So then we reevaluate the metrics and do that on a continuous basis, right? So we learn that. So maybe in the first pass, without any backtracking or we would not be able to do that. But with this iterative process, we actually get to that and identify that. So we are coming up on time. I don't see any other questions. So I guess I will hand it on to the next set of presenters, and we are going to talk about optimizing Kubernetes applications for performance and cost. So thank you, everyone, and hope you stay on for the next sessions here. And thank you, Tsahi, for your insights.
Thanks. Thank you.